Thanks for the introduction. Yeah, I'll just start off by recognizing that there are a lot of people who participated in the Deep Wave campaign. I've just listed a few of these participants who have collaborated on this particular research, but we'll point out that many people contributed, and also thanks to the NCAR EOL team for helping to make that happen as well. Today, I'm going to focus specifically on orographic gravity wave variability and give a few examples of what we found during some of the research flights. So a quick overview, in case you aren't as familiar with the Deep Wave campaign. It was a flight or a campaign using the NCAR Gulfstream 5. We flew out of Christchurch, New Zealand in the New Zealand winter of 2014, so June and July. There were 26 different research flights. Some of them went over to Tasmania, some of them went to the Southern Ocean. And this particular location was chosen because it's called a gravity wave hotspot, or an orographic gravity wave hotspot. So the flights that I'll be focusing on today, while there were many other flights, are specifically looking over the region of the South Island of New Zealand, so really focusing on orographic gravity wave generation or mountain wave generation. Now, there were many instruments available during the Deep Wave campaign, but I'm going to mostly be focusing on the LiDAR systems and the Advanced Mesospheric Temperature Mapper. So on board, we had a Rayleigh LiDAR system and a sodium LiDAR system that were both developed at GATS, and as well as the Advanced Mesospheric Temperature Mapper. So we've got things that are giving a vertical profile from about 20 to 60 kilometers, and then a vertical profile, again with that those sodium returns from about 80 to 100 kilometers. And then the Advanced Mesospheric Temperature Mapper, developed by Mike Taylor's group at Utah State University, gives us spatial temperatures of about 100 by 80 kilometers or so. And that's going to give us information about phase speeds associated with the wave and the extent of the waves as well. So I think that Biff might be here, so if he's here, he's the one that built the sodium LiDAR. So he built the sodium and the Rayleigh LiDARs. Hi, Biff. So those are the instruments that I'll be focusing on today. There were also numerous other instruments, especially flight level instruments, that we've used in this data as well. But these instruments are useful because they're giving us a whole picture from what's going on lower down in the stratosphere all the way up to that MLT region. Something else I'm going to point out is that most people are familiar seeing LiDAR with things that are moving through a stationary beam. So this is a little bit different here, as we're flying through these the orographic waves where not necessarily, we can see things that would be stationary. So we're seeing something different. We're looking spatially instead of temporally with these LiDAR measurements. So a quick overview of just the topics I'm going to discuss today. I'll talk a little bit about some of the secondary gravity wave generation that we've seen during the Deep Wave campaign, and then go into some of the spectral momentum flux that's associated with many of these mountain waves that are generated usually in multiple different scales at once. And then I'll end discussing some of the more complex events that we're still digging through. There's a lot of work to be done, and it's difficult to pull some of these apart because there's just so much going on. So this is going to be providing results for a long time from now. But to start, I'll talk about this secondary gravity wave generation. And when I'm looking at this secondary gravity wave generation, I'm essentially answering the question of, well, how do these gravity wave hotspots actually influence the middle atmosphere and the upper atmosphere? How do they have the potential to influence this? Because orographic waves can only propagate so high, and a lot of these hotspots are associated with orographic gravity activity. So when I'm looking at secondary gravity waves, I'm essentially answering that question. And so to do this, I'm just going to be using some of the case studies from the deep wave campaign. And of course, there has been numerous research done on secondary gravity waves, especially on some of the generation mechanisms. There are several different types of generation mechanisms, and I'll point out that Sharon Vadas over at NWRA has come up with the theory and the math behind the linear generation mechanism. And that's a generation mechanism that generally results in something with a larger horizontal wavelength, lower momentum flux. But there are also other mechanisms that we're starting to learn more about, especially as we get modeling with higher and higher resolution. And this is more of a nonlinear generation mechanism. So this would be something where we're seeing gravity waves on multiple different scales. They may be generated by coupling into instabilities or some other method, but it's not as well understood from the theoretical standpoint as the linear generation mechanism. So right now, this is kind of a hot topic right now because we know that the gravity wave spectra do change throughout the atmosphere, and secondary gravity waves are something that they aren't as well accounted for right now, especially with all the different generation mechanisms and the high resolution that would be needed to resolve some of the physics behind these generation mechanisms. So it's definitely an area of interest. So as I mentioned before, we have these orographic hotspots, but then there's the question of, well, how do they influence the upper atmosphere and the MLT? So we have the mountain wave generation. Mountain wave is vertically propagating, and for the most part, it's stationary, although they can advect and they can, as they're being formed, they can have different phase speeds. But for the most part, once that mountain wave is formed, we assume that it's pretty close to being stationary. And then from gravity wave saturation theory, we do know that the gravity wave amplitude is going to be limited by the background wind. And in the case of mountain waves, we have that where we have a zero or close to zero phase speed. That horizontal wind perturbation is going to actually be directly related to that mean background wind. So then there are two kind of problem areas that would limit orographic wave propagation. And the first one is in this lower region of the atmosphere. Chris Cruzy, who is also a participant in the deep wave campaign, coined the term the mountain wave valve layer, because it doesn't necessarily stop mountain wave propagation in this wintertime hemisphere, but it can definitely limit propagation, or it can cause some dissipation as these mountain waves are propagating through this region. So this is the first problem area, but it's not going to necessarily stop any kind of orographic wave from propagating to higher altitudes. And the second problem area is where we get that zonal wind crossover near 100 kilometers or so. And that's a critical level for mountain waves and orographic waves, so we get a lot of breaking up in that region for those that do make it up to that region. So I'm going to give two different examples of breaking. One where we're seeing breaking lower down in the atmosphere, where we're seeing some influences from that valve layer, and the other one where we're seeing mountain waves that have been able to propagate all the way to the MLT region before breaking. So starting with some of this breaking in the stratosphere, this is a case from the 29th of June. It was a day that was considered to be a very high forcing day. So we had a lot of winds that were blowing down near the surface, generating mountain waves. This is output from the WRF model, and here it's showing that we do have some orographic waves present. We also have that valve layer present. This is also shown by some of the radiosonde measurements as well, that valve layer is indeed present. What's interesting is that we have passes across across the island, and we're able to see some of these orographic gravity waves. Now, they aren't the best formed gravity waves in this region that we saw in the campaign, but you can definitely see this phase structure. Strongest on the first pass, and then we start to see more of this dissipation. The wave is breaking up, and we start to see these other features in the region where the mountain wave is no longer. So as that mountain wave seems to be disappearing or dissipating, it seems to be replaced by these smaller scale features. And in fact, when we do wavelet analysis on this, we do see a shift, a spectral shift. Not for that first pass as much, where we see that mountain wave is fully formed. We don't have data from before then because we just turned on the LiDAR, but we do see as soon as we turn on that LiDAR, that mountain wave was pretty well formed, and it maintains that mountain wave spectra up near 45 kilometers and similar down lower. But on these other two passes where we see the wave is breaking and not fully formed at these higher altitudes, we see a shift in spectra. So we see the mountain wave at lower altitudes, and then near 45 kilometers, we start to see a spectral shift to these shorter wavelengths that are smaller than the original mountain wave.
What does a wavelet analysis in which way is that?
What do you mean?
Well, you apply then a special filter, spectral filter to.
Oh, so I'm just using the Morley wavelet analysis, and so it's taking a wave packet with differing horizontal lengths associated with that, and it moves it through and looks for the correlation. So the higher spectral power is where there's a match between that wavelet. It's a sinusoidal wave.
I see.
In the horizontal direction.
In the horizontal direction, correct.
And you will split it between which wavelength? So you said one shorter and one longer?
The range of wavelengths on the photographs.
Ah.
Oh, yeah. Okay. Yeah. So it's done for a range of wavelengths, and then the spectral power, the higher spectral power, is where you have a better match or correlation between that particular wavelet packet.
Yeah. Now I understand the graph.
Okay. So what we see here is we see a shift in spectral power. So right here, that's about 100 kilometers or so, and up here we see there's still some spectral power associated with that mountain wave, but here these shorter wavelengths start to appear. So kind of giving an overview of what's happening, we have the mountain wave generation. The mountain waves are encountering the valve layer, but not only are they encountering that, they're continuing to experience this limit in amplitude. And it appears that as that mountain wave is breaking, we're replacing this by these smaller scale waves that may be forming with this process. You can see here with the WRF model output, these mountain waves, you can see the mountain wave forming, but the amplitude, instead of increasing, it's actually decreasing, and then up from about 20 to 30 kilometers in altitude, it's not even growing, where you're having that limitation in the wind, and then it's above that region where you're starting to see that breakdown of the mountain wave. So this is an example from the stratosphere, but we also have examples of observed mountain waves in the MLT region, and this is from a case from the 13th of July 2014. I will also talk about this again. There were several different scales of mountain waves present, but the one that was most visible was this 240-kilometer mountain wave observed all the way from 20 kilometers to 87 kilometers. So here's the Rayleigh LiDAR temperature perturbation. You can start to see that those really small perturbations of only a degree or two near 20 kilometers. So it's a very small amplitude generation. This was actually a low forcing event, so there wasn't a lot of activity. Not a lot was expected to happen, but yet this low forcing actually resulted in mountain waves that were able to propagate all the way up. And we can see in the Airglow layer, centered near 87 kilometers, that this 240-kilometer wave is present. Now, of course, as expected, we do have a critical level for that mountain wave. This is the Kingston Meteor Radar data showing that near 90 kilometers or so, we have these winds reduced to near zero. So any orographic waves are going to break as they're approaching that point. I mean, there's a huge shear and decrease in wind leading up to that. And actually, in looking at the sodium mixing ratios, you can see these are averaged over 40 kilometers, so we're not getting all the features, but we are getting that 240-kilometer mountain wave. And we can see that perturbation is visible lower down. This is very unusual for sodium to be perturbed, the layer to be perturbed that much. But by 90 kilometers or so, we're not seeing any evidence of that wave. And this is a huge wave, so there's a lot of momentum deposition associated with this breaking. Another thing I'll point out is that this wave persisted for a period of several days, from what we understand from modeling, and also this was persistent over about 4 hours, the whole 4-hour period of the flight. So this is something that was the wave packet that was being continuously generated over an extended period of time. Now, in looking at some of these other features associated with that wave. So here's the AMTM. So we have the Airglow images. We also have the temperatures associated, and you can very clearly see this 240-kilometer wave. But there are also a lot of small-scale features, especially associated within the warm phase of this. And that's quite interesting. That's something that was unique that has come up during this campaign. It's not just that we see this wave breaking. We also see these smaller scale features that also appear to be waves that are propagating. They have phase speeds. They have momentum fluxes. And when we look at the sodium density perturbations. So this is a day where we had high resolution sodium density measurements. That means we were able to get sodium densities every second, but we were not able to get temperatures. And we could see these smaller scales present, and these are ranging anywhere from about 10 to 40 kilometers. So then the question is, okay, well, see all of these different features. What's going on here? Are those just waves that are happening? Where are they coming from? It's especially apparent where this wave, in the warm phase of the wave, where that sodium is very perturbed. So what we...
This is done with the LiDAR?
Yes. So what we did is, the best way to answer that question is to have a modeling component with the data component. So my colleagues Chris Heel and Jonathan Snively at Embry-Riddle University actually modeled this event, and they have sodium densities in their model. And so this was published in Heel et al. 2017, their simulation of the wave. And then we were able to actually look at the sodium densities and see what was going on as this wave was breaking down. And it's very interesting that we see scales that occur that appear to be from instabilities that seem to couple into secondary gravity waves. And these occur with the breakdown of the wave, and they are on the same scale as what we're seeing in the sodium density that were measured during the campaign. So that brings up some interesting points about some of these nonlinear generation mechanisms of secondary gravity waves. So just to give an overview of this before I move on, we're observing these gravity waves during the deep wave campaign that appear to be associated with a breakdown of mountain waves. And they're occurring at smaller and sometimes similar scales to the primary breaking mountain wave. And so we know that there's the existing linear theory, but there's also this non-linear aspect that may be happening as well that's also generating secondary gravity waves. So this is just some really interesting findings. So from that, I'll move on to the spectral momentum flux associated with some of these mountain waves. I'll focus on two events. I'll talk about that 13th of July, the multi-scale mountain wave event, and also another event that's also a mountain wave event was the 30th of June. So both of these are within a few weeks of each other. But before I talk about that, in order to calculate the momentum flux associated with these mountain waves, there are some things that we had to do in order to get to that point. And so the biggest aspect of this is trying to get the perturbations associated with these observed mountain waves. So we have background winds that we get from the NavGem model and from the ground radar in Tasmania. We can also get background temperatures from SABRE, or there was also a ground-based Rayleigh LiDAR and Lauder. And we also have the background temperatures from the sodium LiDAR when temperatures are available. So when we were running in the high resolution mode, we didn't have temperature measurements. But when we were running in the 2-frequency mode, which took place during the first half of the campaign, we were able to get these background temperature measurements. But where the complexity arises is getting the really high resolutions. So when we're making 2-frequency measurements, you have to average for a significant period of time. And that every second that you're moving on the Gulfstream 5, of course, that's a second that you're losing of spatial resolution. We were doing 2-frequency measurements every 12 seconds, so it's really hard to get some of these high-resolution waves. But another method to do that, especially when we were running in the high-resolution mode, is to actually look at the sodium densities themselves and look at the gravity wave, the parcel displacement, and from the polarization relations derive the temperatures associated with that. So there are two ways of doing that. We can either look at the mixing ratio and look at the parcel displacement. Another way of doing that would also be to look at the shape of the sodium layer itself, as it's a minor species, and calculate what that perturbation amplitude in the sodium density layer corresponds to as far as a temperature perturbation would go. So I have used both of these, and I will focus on that mixing ratio one first. As I mentioned before, my colleagues at Embry-Riddle University actually simulated that first mountain wave event. So we were able to apply some of these techniques to try and validate them. So this is the mixing ratio technique. You can see, especially on the lower side, the mixing ratio is a better method of getting of obtaining the temperature, because as you start to diverge from that layer, it's hard to get what the background sodium density is. So you can see here is the actual temperature, and here the actual temperature is in red, and then the mixing ratio derived temperature is in black, and then the density perturbation lower down at 75 kilometers is not as reliable, but you can see further in the layer there's a little bit of a better match. Now, of course, this is an underestimate, and it is an average. So for instance, here you can see there's a slight evanescent layer in their model, and this method, because it's averaging over the entire parcel displacement, if you have a wavelength that's very large with respect to some of these smaller effects like evanescent layers, you're not going to get them. So this is more of an averaging.
So in this mid graph, the bottom, that's the sodium density itself, not the perturbation.
That's a sodium density that is perturbed, right? So
only the perturbed density.
Yeah, so this is the sodium density total that with the gravity wave propagating through it. And so from that we can actually calculate the mixing ratios. And I applied a calculation that would be similar to what we use on the deep wave data, and then from that we can calculate this sodium mixing ratio, or sodium mixing ratio temperature, or the perturbation from that displacement of the mixing ratio. So when applying this to actual data, we have contours associated with the mixing ratio. We're getting an average or an estimate of these temperature perturbations. So here we have a contour. Then we're able to look at the displacement from the average altitude. From that, with some information about the background atmosphere, we can determine what that temperature perturbation is, and we can get an estimate of what those perturbations look like. This is an example for the particular pass, just using those perturbations. So just that's an average. So that's.
So the temperature, I thought, is directly measured from both the imager and from LiDAR, right?
So the LiDAR, the LiDAR has a 2-frequency measurement, but the problem is getting the resolution while in flight to get some of these smaller scale, especially when we're looking at less than 100 kilometers. It's very difficult to get the resolution that high. But when we do have those 2-frequency measurements, it's actually quite useful because we have the background temperatures that a displaced parcel is going to be experiencing from a gravity wave. And then in this particular case, we were running the LiDAR in a high resolution mode, so we were getting measurements every second, but just from one frequency.
Peak of the each wave line. Stay locked on top of the line.
But the imager, is that considered average, so it's
Yes.
not accurate?
So it's average, and I actually have a few plots later on showing this method. The average, if we do a weighting of these perturbations, overlapping them with the imager, it actually overlaps pretty well. But yes, that's another aspect, is that imager is averaging over a significant range. And so I wanted to look at what's going on in altitude. So doing applying this method to each of the passes, we could get a spectral temperature amplitude, an average temperature amplitude for each wave that is present. So we get a plot like this, and this is very useful because we need it in order to calculate the momentum flux, which is shown on the next slide. And what we see here is that there's this 240 kilometer mountain wave, but we also have contributions that may be harmonics of this mountain wave or just other mountain waves that are present that are at 80 kilometers and 100 kilometers horizontal wavelengths. These have fairly significant momentum fluxes. The momentum fluxes do vary from pass to pass, but we're still seeing that those general horizontal wavelengths are present. So this is just an example of these mountain wave environments and how you can have multiple different mountain waves present.
What is a typical vertical wavelength?
What is a typical vertical wavelength? That's changing in altitude. So near 60 kilometers, you're seeing vertical wavelengths that are 60 kilometers in altitude, where you have a lot of the very strong stratospheric winds, probably 20 to 30 kilometers. But once they're getting up here.
About 81, you have peak oscillation of temperature plus minus 50. What's the typical vertical wavelength?
For near what 81 kilometers? Well, that's a difficult question to answer because the wave is as it's approaching the critical level, it's starting to break down, but probably in that range of 70 to 80, the vertical wavelength is probably closer to 10 kilometers or so, 10, 15.
Kilometers is breaking. It's not propagating.
Right. This wave is experiencing breaking as it's over a whole. I mean, right. We start to see breakdown near 60 kilometers, actually. I mean, the amplitude gets so large. But the wave doesn't necessarily fully break. It can still be propagating and experiencing dissipation. Yes, definitely, and certainly with the model we see the wave is starting to break down, and it's limited by multiple factors. You're right, it is breaking, but we still see evidence of that wave up near 87 kilometers. But by 90 kilometers, it's totally gone and it's totally dissipated. So this is another example of a different mountain wave event. And these are just some of the different passes over the island. And we see in the temperature, in the Advanced Mesospheric Temperature Mapper and in the Airglow, we see some evidence of a mountain wave. And I will do a close-up of some of these because sometimes it's difficult to pull out those perturbations when they're imposed on the background. But this has a wavelength of about 80 to 100 kilometers or so. And when we also see this in the sodium densities. And so if we calculate the temperatures, again, from looking at the sodium densities, we see this has a fairly significant amplitude associated with it. And in fact, when we overlap and weight this, or not weight it, but here I have not weighted it because it's at a lower amplitude. But we do see that the Advanced Mesospheric Temperature Mapper may be sensitive to some of the perturbations of this wave on the lower side of the layer. So this is an overlap with a mixing ratio derived temperature perturbation at 78 kilometers and up to 82 kilometers, and you can see that overlap there. So this is actually was most strongly visible and present on these two consecutive passes. You could see here these three perturbations, and you see again these three perturbations. It appeared from the Advanced Mesospheric Temperature Mapper movies that this particular event was a stationary event, so it appeared to be an orographic wave. And when we do a similar calculation or try and estimate the momentum flux associated with this, we see it's mostly contained just within this wave. This is the main wave that is present. And when we look at the Kingston meteor radars, they are quite far away, but we're still showing a critical level here. So that wave, and again, there may be some variability in these winds, but it's showing that these waves are probably not going to be able to propagate very high. In fact, you don't see this wave anymore at 84 kilometers, and you start to see this wave is pretty much starting to be dissipated by 82 kilometers. So that's a pretty significant amplitude mountain wave that is forced to break by that critical level. But on this particular case, it looks like most of that spectral power was contained more in that 80 to 100 kilometer range. So moving on from this, I'm going to talk about some events that are a little bit more complex where things are not as straightforward. And I think this is going to be more of an open-ended, showing you a few things from the deep wave campaign rather than tying it up neatly, because we had a lot of data and not all of it is a perfect, nice mountain wave event that's easy to interpret. So the event I'm going to talk about is from the 1st of July 2014, and this was considered to be a very high forcing day. So a lot of activity taking place. And these are just a few example plots, and I'll show some more, but you could see there are actually different scales of waves that are seen in this MLT region and the sodium densities, as opposed to the temperatures measured by the Rayleigh LiDAR down lower into the stratosphere. You could see that while there are some significant wave perturbations present, there's also a lot of other stuff going on. So it's really hard to pull all of that apart. But I will at least try and give some sort of characterization of what's going on. So these are some of the observations in the stratosphere. We're seeing scales that are mostly in the range of 40 to 90 kilometers horizontally. there is some evidence on that first pass of waves that are about 120 kilometers or so. But for the most part, these seem to be pretty small scale waves, or smaller horizontal scale waves in that range of 40 to 90 kilometers. Now, what we can also do is we can look at the propagation direction. So again, because this is a LiDAR measurement that is going through, if we look at the different phase orientations, they're not telling us necessarily upward versus downward, but the orientation, the propagation direction of the wave itself. So this would be things that may be propagating westward. These would be eastward. Of course, you can also have things that are downward propagating to the east, or westward propagating, or downward propagating to the west. I can't differentiate that from this data, but we can show that there are definitely waves propagating in different directions and different orientations. And these wavelengths are also quite similar for both of these propagation directions. Now, another question that comes up is, well, what is the variability between paths? If we have orographic waves, we'd expect them to not be moving much, although some advection can occur and the wave can be changing in nature and its amplitude. But for the most part, we expect an orographic generation to have a similar orientation from pass to pass. So for this particular day, we'd also expect orographic waves to have a westward phase orientation. So we see there's a very much a stronger response for the westward orientation versus the eastward orientation. We also see a stronger correlation between the passes for the westward orientation versus the eastward orientation. So this may be telling us that there are orographic waves present, but there are also a lot of other waves present. In fact, there are probably even other waves present that are westward propagating as well. Now, if we do something similar looking at the sodium LiDAR data and the temperature perturbations, there's a lot of variation. We do not see the same scales from pass to pass even. So here in this first pass shown, we see a longer horizontal wavelength wave. This is there was significant wave activity observed. We see both eastward and westward phase orientations. This is more looking at 120, 140 kilometer horizontal wavelengths. But just turning around on the next pass in that period of just 20 minutes or so, we start to see the spectra is changed significantly. So we start to see those shorter wavelengths that are visible at the lower altitudes in the stratosphere. They may be waves that are propagating from the stratosphere, or they may be waves that are generated nearby. But we do see two interesting things here. The first is we see these shorter horizontal wavelength waves around 40, 50 kilometers or so. But then for the eastward phase orientation, we still see a lot of spectral power contained in things that are closer to 140, 150 horizontal kilometers horizontally. We see that for all of three of these eastward phase orientations for each of these passes, but we see a lot of change occurring in those westward phase orientations. So that's something that is still unclear to me as what the source is, but there could be a lot going on there. I mean, we've got a lot of the orographic waves present. Martina Bramberger also just wrote a paper about about the orographic wave generation for this particular flight down lower in the troposphere and the stratosphere, and those waves being generated there. But we also have the potential of reflection occurring, secondary gravity waves occurring, and possibly other sources of these waves. And looking again at the imager data, you can see again this variability between each of these passes. And I'm going to, on the next slide, zoom in on some of these Airglow images to show you the details on that. But there's, in addition to a lot of other waves being present, there is evidence of orographic waves present. So you start to see during this pass right here, one stationary phase. On this next pass, these waves appear to be stationary as we're moving across the island. and as well as these. But then you also have some other waves that are moving in both directions, not just one direction or the other. And again, here's that following pass. You still see one stationary phase, but you also see a lot of other movement of wave activity. Also, this up here appears to be a sawtooth pattern that you would see with a wave that is approaching breaking. So this also appears to be some sort of orographic wave as it's stationary, but it also appears to be breaking. So you're getting a lot of wave propagation, breaking, likely secondary gravity wave generation. And just to follow up on that, I think you had asked about the advanced mesospheric temperature mapper measuring temperatures. This is an example of the sodium density derived temperature perturbations and weighted near the altitudes of where the Airglow is expected to be. And you can see what these perturbations look like overlapped with the advanced mesospheric temperature mapper perturbations. And you can see the variability once we start to get all of these smaller scales. So it's just it's difficult to determine which altitude is coming from where, because there's a lot more wave activity here, and some of the larger scale waves are matching up, but just there are so many waves that appear, and just over the period of just a very short time of less than a half an hour. So you're getting a lot of variability. That could be from many different things happening. I'll also point out that in addition to variability in forcing conditions or variability due to constant wave breaking as these orographic waves are being generated, we're also getting changes in the background environment. So this is the background temperature derived from the sodium LiDAR. This is a day where we had 2 frequencies. And you can see, especially where we see this strong activity, we also have a strong temperature decrease from about 85 kilometers up to 95 kilometers. So that could be playing a role in some of this as well. But you can see there's a lot of variability in the background over just a few hour period. So to sum this up, to tie this up, when we're talking about some of these multi-scale environments, some of them have nice conclusions of this is a mountain wave that we saw, but then there are these other events that are still really worth digging through. The complexity is very intriguing. And I think there are a lot of questions that still need to be answered about where all these waves are coming from, whether it's the changing conditions in the stratosphere or the MLT that are contributing to the variability, or whether it is different forcing in the troposphere. But we still have a lot of analysis to be done, and in many different interesting cases. So just again, acknowledging all the colleagues and collaborators on this. Again, Biff is here. He built the LiDARs. And at this point, I'd be happy to take any questions.
Now, if you take the sodium layer and look at it vertically, where would be sort of the maximum of a response when you point a laser on it?
A maximum response for density perturbation?
For the globe.
For the Airglow?
Yeah.
That depends. So, I mean, there have been studies showing that the Airglow is centered near about 87 kilometers. On this particular, just during several of the flights on this particular campaign, Sabre was showing that the layer was getting down to as low as 80 kilometers. At one measurement showed it at 78 kilometers, which is the peak of the Airglow. So it's very unusual, and it's a difficulty in trying to overlap the 2 measurements.
Yeah, I'm asking this because certainly we know that the Airglow layer is used by nighttime astronomy to create an artificial star as a point source that's being observed at the same time as a piece of the sky. and by using adaptive optics to get this point perfect, they have a correction for the adaptive mirror. But if there is large variety fluctuation in the Airglow layer itself, then this assumption that you have this stable point source that is like a point source out in space will not work anymore. So I register this with interest and will see. So this is in the aftermath of a really big disturbance in the troposphere.
Yeah, so this is over the area of like a gravity wave hotspot area. So sometimes the Airglow is pretty boring.
Halfway around the world to find a place as bad as possible, or as good as possible.
And the sodium density itself doesn't move as much as the chemically excited Airglow.
That's what I was going to ask. The peak of the Airglow layer is not the same as the peak of the sodium.
No, it varies more temperature.
And the LiDAR is going to illuminate the sodium directly.
Yes, no, we measure the sodium backscatter.
Right. So the location of the LiDAR illuminated sodium responds to the sodium layer itself, whereas the Airglow layer responds to the combination of sodium and all other sort of stuff.
Yeah. You do get perturbations, especially from tides over longer periods. The centroid will move by 5, sometimes 10 kilometers for larger tides. So your distance is changing in terms of the guide star question. These short period perturbations mostly perturbate strongly the lower edge of the layer. The center is not affected nearly as much. But yeah, for the average peak will change over 12 or 24 hours by 5 kilometers quite often, depending how big the tides are.
Thank you.
Yep.
So in the beginning, especially, you were comparing your observations to the WRF model.
Mm-hmm.
Is the WRF model showing just the physics of the model, or is it assimilating a lot of data, so you're actually showing a sort of a combination of physics and whatever data is assimilated into that model?
So Chris Cruzy ran the WRF model for the entire deep wave campaign, and he used ECMWF to run that model. I think he's published those results in a 2016 paper, but I'm not as familiar on that front.
Yeah, this data is all independent of the model.
Well, I was just trying to figure out what the comparison was showing. You've got data agreeing with the model. Does that validate the model, or is it?
Yeah.
Well, I mean,
A bit of both.
Okay. Yeah.
so yeah, they're kind of playing off of each other. So ECMWF has been, they've been trying to use that to predict some of these events. And I mean, ECMWF saw that 240 kilometer mountain wave event, and WRF is able to be run at a slightly higher resolution than ECMWF. So.
The upper stratosphere, the agreement with ECMWF was very good, both over the mountains and over the Southern Ocean, looking at jet stream and storm creating waves. Certainly on the larger scales where it's rivals, but we're very happy with the model comparison, definitely in the stratosphere. And the mesopause, that trying to push some of these models up to reach these layers, but there's a lot more variability in what we see, and it's a lot harder to type in. We had hoped to get LiDAR data all the way through, but we have a gap between 60 and 75 kilometers.
So in the modeling of this nonlinear wave breaking is then ultimately the problem, the usual problem, which is the smallest scales that you can't explicitly run in the model, and how you do that. Is that?
If the model has sufficient resolution, I think it should be good down to the scale where it cannot result.
I think the issue would be, accounting for the physics and the global scale models, but they're getting higher.
Scale issue still that you model in some way.
It depends. difference of model, he said it's a DNS, so I'm not sure if he uses that
So
model.
the model I showed was a 2D model, and it has a resolution of 0.5 kilometer in both altitude and spatial resolution. So even that one may not be resolving all of the nonlinear instabilities and wave breakdown, but it's able to resolve some of the 10 to 20 kilometer features that are arising.
Just technical question: how do you define background usually to get perturbation of waves, observation of how the waves are?
How do I determine?
Background.
Oh, yeah. So,
Is it hourly or just 6 hour average, 2 hour average?
It depends on the data set I'm working with, because if you have a very long data set, sometimes I'll just do a running average. But yes, sometimes for the sodium density perturbations that I showed, for the very small scale ones, I did a running average. So even being able to remove stuff that's on the order of over 100 kilometers spatial resolution. What's the temporal resolution of?
What's averaging for temporal? Just your length, average over the length, or what time period that you do?
Yeah, again, that depends on what because a lit average would be about 45 minutes or so. So I've done that with some of the data.
If you, for instance, would like to compare ECMWF output data versus your observation, how you average ECMWF?
And what we did for the comparisons was we basically sampled the ECMWF at the specific flight points and times. It doesn't really have that kind of time resolution, so there's an interpolation in there. But mostly we went through, and most of the variation is horizontal, because you're covering hundreds of, around thousands of kilometers in some of the flight legs in 45 minutes to an hour. So it's mostly a horizontal variation to pick up with the ECMWF model. And that was really good. ECMWF was doing a great job for a lot of the horizontal perturbations and the 100 plus kilometer horizontal waves.
Is it 30 kilometers evaluation?
What'd you say?
The horizontal evaluation of ECMWF.
I think we're looking 16 kilometers. 16. But the DLR has been working a lot on that with the comparison LiDAR. And we also have the DLR Falcon with measurements lower down.
So you have high frequency sampling and you do just sample model without observation points.
That was the first step. And then we go back in cases and look at more of the 3D environment in the model.
So this is a great effort. And having jumped back and forth from modeling and observations all my life, my question would be, with where you stand with this whole analysis, are there already areas identified where you can tell the modelers you have a problem, you need to, there's something missing? Or is it that one just has the feeling it's an issue of getting more resolution?
I think there are probably different aspects to answer all of those questions. I mean, coming up with data that shows that non-linearly generated secondary gravity waves are an important factor is that's something that hasn't been seen a lot before. These are new observations. That can be something to relay to the modeling community, but may not improve a model. Whereas a lot of this data is also being used, and we're working with ECMWF and NavGem to improve those models with assumptions about the gravity wave drag parameterization and getting the winds and the MLT to match up. So there are lots of different aspects to that. I think some of them is more or less just bringing up a new issue that hasn't necessarily been observed, and the other part of this data is more.
Yeah. That's exactly what I'm after. All these parameterizations, one he doesn't want to know.
If you have a gravity wave resolving model with sufficient resolution, in principle, it will resolve nonlinearities and secondary waves. Right? I mean, there's some things, right?
This is a good work.
You're asking, is there some fundamental physics thing missing that have to be put in? Well, I'm thinking that it's still just fluid dynamics, you know, molecular breakdown level.
Yeah, just, I mean, naively, could it be that there is a chemical ingredient missing that you haven't identified that plays a role in the system? It's something like that. I don't know. I'm just curious.
From the perspective of the thermosphere effects, the great imponderable is what happens when you do truly get sub-grid scale. Half a kilometer resolution, that energy and momentum continues to turn itself into mixing. And of course, what we would like to know is what comes out after all the dynamics are finished. What's going on at 105 kilometers? That's an area where we don't necessarily have the process. Parameterizations are still going to come into play. Regardless of how much resolution.
The ECMWF is adjusting their parameterization now. The initial comparison was that they were just coming out with a new parameterization in 2014. The first comparison, the version before that was a bit better. And they've been very good at predicting the waves, but the amplitudes were underestimated in quite a few of the cases. But the phases and locations were quite good. I haven't looked at that in the last year or so. DLR's been taking the lead on that. They're actually going through the parameterization.
What's the upper height of the EC?
It's a sponge layer, maybe 60.
Oh, so
It's the really lighter comparison between 30 and 50. That's the focus for that. And then we're looking at some
About the
something.
gravity waves or all of station.
For those, since we're looking at the large horizontal scale, like the 240 kilometer wave she's talking about, showed up very well. And then we're looking at more for NavGen for the higher resolution. The smaller scale.
And you're using this European model and no American model?
NavGen.
NavGen, the Navy model. NRL was a big partner.
Navy, global environmental model.
But you seem to refer to the ECMWF model sort of as the standard.
Well,
I'm picking that up.
DLR was
Is that a fair
a big
assessment?
partner in the project. So they brought a lot of it. Yale University was a partner as well, and they focused more on the WARP and other smaller scale mountain wave models. But DLR brought in the global scale model with their own funding. So give me a large amount of downtime.
And then you fly again.
Will we fly again?
The next deep wave campaign.
We proposed for a chemistry-focused campaign on stratospheric chemistry 2 years ago, but that was not chosen. So we're looking at partners for the next campaign. So if people have ideas or want to participate, Dave, for instance, has been talking to various people, but the instruments are available to fly again. The problem is the last campaign was funded through Aeronomy in large part, so going back to Aeronomy soon would be difficult. It's very expensive. So navigating the politics and probably best if we had another PI with a different science question aside from dynamics would be good.
Yeah, I would be curious whether this would apply to Hawaii. kind of work?
Yeah, we've had discussions with it. This is actually a guide star laser with blue. It's very much smaller than traditional sodium systems. So I did modify it to do range resolution. But yeah, we used a system that's the same as deployed in 6 of them down at ESO in Chile.
Yeah, I've seen them running 4 at a time.
Yeah, we could only afford 1 at half hour for a run.
Yeah.
No more questions? Thank you again.
Yeah,